1 does not have a lot of integration as mathematical operations that are necessary to answer questions. There's only like 4 or 5 times where I'm like, okay, now we have to integrate something. It's rare. Most of the time we're going to do derivatives. Regardless, let's start with integration. And just to remind you, okay, there's an integration symbol. Now, pchem 2, by the way, that is all integration. Now remember that actually, look, not trying to make fun of anyone, but there were a couple of people last semester who thought that this was the number 2, not a partial, not that funny, but anyway, so that's a partial. Now partials have to be integrated, right? And this is what I'm integrating. So recall that, integrals, it's like, actually I learned this from an educator, that multiplication is easier than division, even though they're technically the exact same thing. And integration is actually harder than derivatives. Derivatives are easy, but integrals are like, I have to do the derivative backward in my head. So I take the derivative of what to get 3x? Now, of course, I know the little power rule, so there's going to be a squared. The square is going to be coming down, so I better get rid of that. The 3 has gone nowhere. Okay, of course, the derivative of x is 1. That's where the 1 came from, minus minus. And of course, I have to consider that there's a constant left over, which in the physical sciences is never really true. There's your answer, unless that was an indefinite integral. Here's a definite integral. Again, hopefully this is all just knee-jerk response, and if this is what I asked, then let's see, I've got 6 minus 2 is 4, 0, so that's 4. Okay. Anyway, look, real basic stuff, but if you're looking at this and you think this is a 2, okay, look at my little calculus link, and you cannot do that. You've got to be able to do this. Now, here's 2 that we will run into a fairly large amount. Actually, well, again, there aren't many integrals, but when we do integrals, you're going to see this guy a lot. What is this one? You're right, natural log. Remember that the derivative of natural log is 1 over x, and therefore integrals, right, you have to kind of work it backwards. I don't like that. Here's one that I'm going to use in another minute. And we're going to see a bunch of this in pchem 2, and I'm not beyond getting you ready for pchem 2 and pchem 1 because it's kind of hard. Now remember that the exponentials survive taking derivatives. All right, but you're going to bring down the argument of the exponent, and so that has to be divided out. So there you go. Now, generally, when it comes to integrals and derivatives of exponentials, I just look at Wikipedia. On the test, if you have one, I'll give you an identity. Because why would I expect you to memorize something that you can look in Wikipedia and get the answer in like 20 seconds, maybe 10 seconds if you're really fast with your thumbs? Anyway, if you can look at Wikipedia and get an answer, I will provide it for you because that's why we have Wikipedia. That's why we made the internet. So identities like this, if you need them, like a harder one, I consider this a harder one. Seriously, I do. It's trivial, it's childish, but I consider this a harder one. It'll be on the cheat sheet. Okay, hardest one of all. And we're actually not going to do it in this class because of ways I've changed it, but I've already written my notes. So I'm going to do all my notes. But this is a good reminder, integration by parts. So if you have an integral of this nature, where there's kind of 2 obvious functions that are disparate, obviously a linear, and here I've got 2x, and of course I have to have a partial. Partials have to be integrated. And here, this is a difficult one because I have 2 functions that really are significantly different in their mathematical form. So what I want to do is remember integration by parts, which goes like this. I got a function times the derivative of a function. And of course, there always has to be a partial. And that is equal to the functions, minus another integral. And the funny thing about this is it always strikes me that the integration by parts actually makes the question harder because it's bigger and there's still an integral. The answer is that it's perfect for the right question. If you figure out exactly what to make f and g, even though this is relatively simple compared to this, pick your battle just right, it actually isn't. That's the kind of cool thing about math, in my opinion. That's why I live alone. Okay, so now an obvious candidate for f is x plus 1, and it survives the integral, right? So it still has to be there, and therefore I do need to know this, and so that becomes very easy. The one that's a little bit more difficult is identifying the derivative. Well, now since I've decided f, then the derivative of g with respect to x is automatically the leftover. Unfortunately, now what I have to do is integrate, right? Bring the partial over and integrate both sides to get g is equal to the integral of this. And if I look at this identity right up there, yes, I did them in order. I'm actually that well prepared and planned. I recognize it to be this. There you go. Okay, so, oh, sorry, I try not to do it this way, but let me just do it this way anyway. Okay, this ends up being x plus 1, and so I'm doing this f and g, e to the 2x, all over 2. And now I've got an integral left over. G, okay, I'm integrating e to the 2x over 2. Df dx is 1 dx. And this ends up being, again, the first part is left alone over 2. And the next guy is, I just use that formula up there again, and I get e to the 2x over 4. Again, integration by parts is nice if you pick your battles just right. Now again, we won't use it in this class. I just want you to look at this and say, yeah, I remember how to do that. If not, not good. Even if I'm not using this, this is the level you absolutely must be at in terms of your comfort. Okay, so blah, blah, let's get rid of integration because we're not going to do that much integration. We're going to do differentiation. Let me start with some regular identities. I'm counting on that you already know the derivative of x with respect to x is 1. The derivative of y with respect to x would be 0 because y is not x unless it is x. In case I have to tell you that. Y is equal to f of x, right? X squared, well, that's 2x, right? Remember, derivatives are easy. That's why keeping 1 is easier than keeping 2. Let me give you some identities, ones that we're going to use a lot. And let's assume that I've got functions x and g. And here's a simple one that does come up a fair amount. F and g, the two functions are added together. I got this. Now again, this is second week of calc class, calc 1. So if this is x plus 1, this is 1 plus 0, right? So I was actually kind of doing that up there. So very simple. Now again, childish, but let me go ahead and throw you the first curveball. For reasons I'm going to start to make clear bit by bit, when I get to multivariable calculus, I'm actually going to take I'm going to make this, I'm going to use a little bit of shorthand. Sorry, I have to give examples. Trying to describe something is not helpful. I just need to give examples, so I need to shut up. Okay, what I'm going to do is I'm going to do a lot of things like this, especially when it comes to multivariable calc. Notice I just wrote the same thing, I just didn't divide by dx. Right, so it's just this, I just didn't write the bottom half. Okay, now let me emphasize one thing really important, this is crucial, you're going to hear me say it 1,000 times. Partials are useless. Partials, what's the value of a partial? Remember? Now these have units, if f is the number of cats, then this partial has units of cats, but it has a value of what? How many cats? 0. Remember that partials are used in calculus to represent a very, very small interval. So small that it's effectively 0. So if this is an interval of cats, it has units of cats, but it has a value of 0. That means that partials are useless. Partials must be either integrated, then they have meaning, and I'm just saying that's regular calculus like you've already known it, or you divide partials by another partial and now it's a derivative, or slope of a line. That's right, you know what a slope of a line is, you knew that since middle school. Calculus, you just learned that it was a derivative. Okay, so notice that I just didn't write the bottom half. Now, I need to, but I haven't written it for a good reason. When we get to multivariable calculus, it's not necessarily clear what I'm going to take the derivative of, because I have two choices, x or y. Again, when f is a function of x and y, I might need to do manipulations that are going to save a lot of time, and at the end I'll decide whether I'm doing the derivative with respect to x or y. I'm sorry, I'm trying to explain it, but let me do examples. Examples are going to be better. Before I do more better examples, let me just remind you of this one. This comes up a lot. F times G. This is the product rule. Someone remind me. I think this is the product rule. Is that right? Yeah. And actually, integration by parts is you take the product rule and you just integrate it again. Take the derivative and integrate it back. That's actually where you get the integration by parts formula. And now let me do this with this weird shorthand that I've just been blabbering about. And in this case, this is F change in G plus G change in F. Again, this is actually going to be really nice to put it this way. If you're like very uncomfortable right now, that's okay. We're going to do so many examples. This is going to actually become more second nature to you than doing it, to be blunt, the right way, in all honesty. And why don't, let me give you one last one. Okay, this is one I hate. Fortunately, it doesn't come up too much. Let's do F over G. I hate doing calculus with what do you call the one things over another? Quotients, yes, quotients. I hate doing calculus with quotients. Here's how I do it. I always put the guy on bottom. I give him an exponent of -1 because I know the power of the law and all that stuff. Just bring down the exponent. So anyway, I just automatically do that. So leave one alone and do the derivative of the other. Next time, leave the other guy alone and do the derivative of the other. Again, you should know the derivative of g to the -1 is minus g to the -2. But then you do the derivative of the inside function, so you still get this guy. Anyway, yeah, there you go. Now remember also, again, last identity before I do multivariable calculus, you've only got, we're not going to do this very often when you have more than one variable. I'm going to just use the letter T in this case. You're actually not going to see this except for that one question on the homework, because this works when you have, this is the chain rule, so I should have written that, sorry, chain. Okay, the chain rule for for a function of, if I have just two variables here, and so you can see just basically what happens is you can kind of cancel these out, and you've got, it's like fractions, A over B times B over C is A over C. That totally works. And I gave you a homework set, but we're not actually going to be able to use this because when you have three variables, X, Y, and Z, then this actually doesn't work anymore, and that will be the case in all the problems that we're going to see. And I'm going to give a big example in a minute. But to do that, I have to unfortunately do multivariable calculus. The thing that you never had, the thing that I'm going to cover, and then it's fair game. You see, what happened was, I really felt sorry for the guy. I didn't feel threatened, but some poor SOB took my class, took 344 without 340. And of course, I'm doing multivariable calc because I have to. As I mentioned, PD equals nRT has 4 variables. I cannot even manipulate PD equals nRT without multivariable calculus. I know you haven't had it. That's why I'm covering it right now. But this poor guy thought he could go complain to the dean. He didn't. The other students convinced him not to because he would have lost that battle because I covered it. So anyway, multivariable calculus. And I know it's its own class. However, this is really easy. It shouldn't even, the scariest thing about this is that it has its own name. If it wasn't for that, no, seriously, that actually makes it worse than it is. Because this is just shockingly easy. Now, again, this is a class of derivatives. I'm not even going to try to integrate with multivariable calculus. We'll do that next semester. Let's just do derivatives. We're going to stick to the derivative half of calculus, and we're going to do derivatives of multivariable functions. Let's do x and y. So f is a function of x and y. And let me stick with that. Let me start out with my slightly odder half derivative. Okay. I know that if I'm going to take the derivative of a function, and we'll do x, there you go. You just take the derivative of with respect to x. Now, technically, I need to take I would have a partial of x as well. You know, this is like a line, right? So f is a line that depends on x. So the way that the line changes is the slope times how much you move left or right, right? You kind of remember that? Again, f is like a line that depends on x. X is the x-axis. And so if you want to know how y changes with x, look at the slope and then multiply by how much it was pushed left and right. That's what this says. Okay, now that's single variable calculus. You already know this. Let's do multivariable calc. What you do is you do the same thing with the other variable. And that's it. No, seriously, that's it. That is all of multivariable calculus, or half at least, that's the derivative half. Seriously, that's all you do. Just do it again, add on a term, and do it again with the other variable. Wow, an entire half a semester, you owe me $500. Okay. Now, there is some notation you have to be a little bit careful of. I'm going to do this. This means while holding y constant. And if I'm going to change y, then I need to hold x constant. Sorry, my x. I changed my x's as I'm writing through. Anyway, okay. Just a little bit of notation. It is actually shockingly important to get this right. So there you go. You want it. You need to memorize this. Sorry. Yes. I'll put a little star. I put little stars by things you've really got to know. This you've got to keep by heart. I'm going to say that very, very infrequently. Let me draw what this looks like. And I'm going to have an x-axis, I'm going to have a y-axis, and I'm going to have f of x and y, which is actually like a z-axis, and I'm not even going to label that. And I'll draw a little bit of a grid. I'll try not to make it too gritty so that you know, hopefully can see it. And yeah, this is one of those times I probably should be PowerPointing. But what I don't like is that if I PowerPoint, you are struggling to write, and I am not. And we get out of step with each other. As you can tell, I get uncomfortable if I'm not saying something without being affirmed or teared. So there you go. There's a little grid, and let me start. Here's where the function starts, and I think I want it in here. Okay, and now you have it kind of in your mind. You have to kind of look at this in 3 dimensions. So you see this line kind of popping out of the board here. The best I can do. Sorry, you know, there's a flat screen. And what this means is one of the things I really want to try to emphasize is that I can look at the mathematical equations and equate them to actions. I will do that all the time, especially when these equations are equations of things that are real. Okay, when I look at taking a step in the x direction, the way I want to do that, actually, tell you what, let me, what I want to do, I want to actually, let's start with this term. Let's start with this term because it actually works with my graph a little bit better. What does this mean? Each one of these bits corresponds to an action. Let's start here, changing y. So what I'm going to do is I'm going to move in y while keeping x constant. And that means I'm moving along this part right here. Right? You see, I changed y, but I didn't change x. X is still at 1. Then this guy is a slope, and I'm looking for the total change. The total change is this right here. Okay, I know it's a little funky, but you can kind of see, I hope you can see what I did. I moved in y, and then I queried how much times the slope gives me how much the function changed, which would be the length of this segment of the line right here. Okay, this was one term. Now I'm at this spot, and now I have to move in x and hold y constant. You see why I started with y? See, now I have to move into the board. I'll draw that as well as I can. It won't be great. And maybe I'll do some video magic or something. Okay, so now I move to the right. Sorry, first I moved to the right and up. Now I'm going to move into the board. And it actually looks like this thing's kind of arching still into the board, so I'm still moving up. to this point, and this part of this of the change of this function is right here. Is that part is this segment right here? Add them up to get the total. Now, of course, this is calculus, so reality is these steps. Sorry, I should have drawn this bigger, shouldn't I? Sorry about that. I'll try to see if I can zoom it in with the video. Of course, in calculus land, these little steps are actually too little. But reality is they're infinitely small, right? So again, expression can be put into action, literally taking a step. So, and hopefully, if you get anything out of this, hopefully you see what I mean by holding this x and y constant. Okay, let me start giving, again, examples. Hard examples are the best way to do this. With x and y, let's start with the function that we'll see most often, x times y. Like P times V, it's energy, right? In this class, thermo? Thermo's about energy. Pressure times volume is energy. I bet we're going to see pressure times volume a lot. Yes, you are. I already know I taught this class 3 times. Okay, I'm being an idiot. Okay, so now what do I want to do? Okay, so let's do this term. Let's do this term right here. The partial, the dx don't change. Okay, if this is the case, then the f of x and y, the change with respect to x, a constant y, is the change in xy, because that's the definition of the function, with respect to x, a constant y. Okay, which is, anyone want to guess? What is it? A constant y. Make the y a number 5. It's y. Okay, here's how you do this. Y is a constant. Now, I tried to do that graphically here. I kind of failed by not drawing it well or big enough. But anyway, if y is a constant, make it the number in your head. You're trying to do this as the test. Make it the number 5. It's 5x. What's the derivative of 5x? It's 5. Okay, but unfortunately, it's not 5. It's y. Call it y. There you go. 5 is y. You see? You know how to do this just fine. This is shockingly simple. The f of x and y, dy at constant x is, of course, x, not y, for the same reason. Okay, and that means, sorry, I'm not using the board super well. I'm doing my best. But anyway, so therefore the change in f, again, is already df dx. I'm just going to write it out again. Just because I want you to get familiar with it, I'm actually just trying to force you to write it again, because God knows you're going to. And I've identified these two parts, so this is y dx plus x dy. Okay, there you go. And, okay, now this is it. This is multivariable calculus. I'm done. Everything else now is just a matter of defining a function. Guess what? I don't think I ever go harder than x times y. It's just going to be p times v. I'm just going to change the letters. Seriously, that's it. Now, remember, I made earlier a big deal of partials are useless on their own. So, right now, I've got a whole bunch of nothing, because everything's a partial, and the partials have 0 value. Here's my point. When we do, here I should have done that before, sorry, being OCD. When we're doing all these thermodynamic manipulations and proofs, I'm going to do it in this half-assed way, because you can see here that I can do some manipulations to make it easier. It's still meaningless. What I'm going to do next to answer the question that will be asked is later I'll be doing this. And don't even write this down. What you're going to do is you're going to figure out what the change in f is, and at the end you've done a lot of manipulation, and at the very end then you'll do this part. Then you'll say the change with respect to x or y, and then you'll come over here and do the same thing. Just not even worry about it. And there you go, there's your answer. Sometimes, again, albeit rarely, sometimes you want to integrate them. That's also what's going to happen. In the end of the day, we either have to take a derivative or we have to integrate a partial. They have to have that happen or they're meaningless. My point is I do it this way because of this intermediate step here allows me some simplification that's just going to make it simpler, just like I said. So anyway, also just get used to it. That's how we're going to do it. Okay, another example, and oh, then I got to do one more thing. Sorry, I'm getting a little slow. Double derivatives, you're going to have a lot of double derivatives. Let me give you two identities that you're going to see a lot. We are going to do some double derivatives kind of soon. And this is just a notation one, and then I have another identity for you that you need on your homework, by the way. So double derivatives. Handwriting is a great skill that you won't improve. Now, when I have two variables, it means I can do derivatives twice with respect to different variables. So let's do df dx, and of course I need to hold y constant. That's a single derivative, so to the outside of that, I'm going to take the derivative with respect to y. If I do that, and then I need to hold x constant. This is simple, it's not a big deal. I just want you to get used to the notation. It's just a little bit different. These guys are a little unusual. Just get used to that and you're done. Here's another identity. Again, this means it's not related. Let's do the x, y. Again, let's hold z constant. Also trying to get you used to x, y, and z, because I'm going to do that a lot. This is equal to 1 over dy dx. Also a constant z. Okay, lesson. Lesson here is that partials can be treated like fractions. All the algebraic manipulations of fractions, a over b times b over c is equal to a over c, all of those manipulations can be done with partials. A over b is equal to 1 over b over a. Right? Not that hard. That's all I did. Here's the tricky thing. The z is still held constant. Even if I flip it, the z is held constant. You need this to answer the hard question on your homework, by the way. Just, there it is. Okay, let's see, what else do I need to do? Last bit, the Euler chain rule. Euler chain rule. That's also on the hard question. I do try to have the last questions on the homework set harder than the others, so it builds up. I definitely do that on the test. The first question is childish, the last question is not. If you think the first question is very hard and you've written a page, you've screwed up because it's not hard. Thanks for helping me out there. Okay, let me redo this df, x, y, and z bit. Let me do it with z instead. Is that a big deal? F versus z? Remember, if we're all speaking Russian, none of this makes any sense because they use a different alphabet. So instead of f, I use the z. And that's just because the formula I'm about to derive is traditionally done this way. And again, I want you to get used to this little expression for multivariable derivatives. Derivative of one thing times plus the derivative of another. Okay, now again, I've been blabbering at length that none of this means anything until it's either integrated or derivatized. I'm going to derivatize this, and I'm going to do this to get the formula that I want. I'm going to take all this jazz and I'm going to divide by dz. Now, here's one of the tricks. This guy, this is a slope. It's done. Leave it alone. Leave it alone. This guy is not done. It's looking for a partner. And so it gets, this is the thing that absorbs the partial. Okay, again, this first term is done. Don't touch it. There's nothing else to be done with it. The y is looking for a partner. So give it to that. Okay, now, remember I'm doing multivariable calculus. I need to hold something constant. I've got new slopes appearing. This dz dx, this dy dx. These are derivatives. They're slopes of lines. And because I'm in multivariable calculus land, I need to pick what's held constant. Now, what do I need to pick? Right? I need a letter. I have to put a letter here. What do I pick? It's a trick question. I can pick anything I want. But I'm going to choose the thing that gets me to what I want to get to. But I can choose anything. But you're right. I will choose y. Yeah, I will choose y. But I didn't have to. If you were thinking, oh, well, because there's no y here, it has to be y. No. No. I could have made it z. I could have said the z dx a constant z. Then I will. I will do that. It will make the whole thing 0, by the way. I digress. You can make what's constant whatever you want. Totally fine. The question is, does it actually make sense? The question is, does it get you to the answer I'm asking quickly? That's the hard part. Okay, so I screwed up. Yeah, I screwed up. I looked at the wrong line of my derivation. I actually do need to hold z constant. That's why it was in my head. Sorry, I meant to hold z constant. My bad, my bad. Okay, what does this turn into? 0, right. Now, if this is confusing you, what's the change in the thing that's not changing? Right? Remember, all these mathematical things can be expressed in words. How does z change when it doesn't change? The answer is it does not. That's 0. Okay, how does this change? How does a change in a meter divided by a change in a meter with something that held constant that doesn't matter? What's this? 0? 1. 1. It's 1, yeah. Change in a meter divided by a change in a meter when my chickens are held constant is still 1, right? So this is 1. And there you go. All right, now I'm going to, sorry, again, the board is a little funky. Let's see. I'm going to actually keep this guy. I'm going to do 2 steps of algebra. I'm going to do a little funky. I'm actually bringing this guy over. And I'm going to leave these other 2. Actually, I'm bringing the other 2 to the other side. I'm just writing it mirror-like. Constant x. Actually, every time I have to use the Euler equation, I just derive it because it's relatively easy. Okay, so there you go. I'll tell you what, let me just get to the answer and then toss it up there because I'm kind of screwing up. I'm kind of running out of time. I promise you the end time is I'm going to kind of blow that. Okay, the end result is called the Euler chain formula. And there is a simple mnemonic to remember it. dx dy at constant z, dy dz at constant x, dz dx at constant y. And if you don't remember that, it's on the cheat sheet. And it's equal to -1. There you go. What's funky about this is that, look, I just proved it. This is true. There's nothing wrong with what I just did. I find this -1 funky. Why? Because if I eliminate the y's and then the z's, I should have dx over dx equal to 1, not -1. Go figure. I've never really understood that. It's very strange to me. Again, you see how like chain rule, so I can get rid of these, and I'd have dx over dx, which would be 1. It's not. It's -1. This is why I was telling you the chain rule that I actually drew up a little while ago. It doesn't quite work when you have more than 2 variables. When you have 3 variables, it doesn't really work anymore. You have to use this formula. Note that I derived it. Let me just toss this up here. Again, sorry about that. Here, board. And the last thing I want to do is use it, and then that's it. I do need to give this example. I'm sorry. I will end on time. I thought I did it a little early. My bad. I've got stuff to do as well. No, then again, I'm just a baby. Oh well. So let me give an example to make this more concrete. The one that you do on your homework is really kind of horrible. Sorry about that, but you can hack that. I will give really awful questions on homework. Yeah, I'm sorry, but I will not give a question that hard on a test. You beat that Greg, right? So let's do an example. Let's do a real gas equation. This is one I just made up. It's kind of like a virial, but I just made it up. It's not a bad equation. I guess none of them are bad. Maybe the equation for nuclear weapons is bad. Anyway, okay, so this is a real gas equation, and what I want is this. I want this. This should be kind of difficult. You are used to y is equal to x squared over x, ln x. Y is equal to e to the x. Y is equal to ln x. Here's your y. It's on the wrong side, right? You need the y over here. Okay, how do you do it? Multiply by y? Multiply by dm? Divide by p? Well, okay, divide by p, multiply by dm. dm is equal to RT over p. What about the dm that's still here? That's a screw up. That doesn't work. You need dm here and it can't be here. And then you do the derivative with respect to t. The problem is you can't do it. Look, there's some tricks, but this is, the Euler chain formula is a way to do this. There are other ways to do it, maybe some of you know them, but this is an easy way to do it. Okay, notice that, let's see, what have I got? Let me just follow my own notes here. If I make x, look at the Euler chain, if I make x be m, y is t, and z is p, let me plug these into the Euler chain formula. And, okay, so dx, which is vm, dy, which is t, at constant z, which is p. Actually, let me look at this version. Sorry, blah, blah, blah. Getting ahead of myself. Okay, that's the first term. Let me go ahead and do some manipulation. I'm going to bring one term over. Let's see. Let me take -1, and I'm going to divide by the I'm going to use this right here. So I'm going to use this right here, and y is t. What have I done? I feel like I've kind of screwed something up here. I'm sorry, folks. I'm just what have I done? What have I done? Sorry. Yeah. I'm going to do the dz dx term. Z is P, dx is dm. Sorry, I was kind of just blanking out myself. Okay, that's the most right-hand term. Let me do the middle term, but I'm going to have to flip it over. The dy, dz at constant x, but I have to flip it over like here. Sorry, I'm rushing. Sorry if this is confusing. I should have started this sooner. dp, the y, which is t, constant dm. Okay, sorry folks, I'm just a little perturbed, and then I tend to spiral out of control. I'm just using the the Euler chain formula. I've identified x, y, and z as vm, t, and t, and I've just done some manipulations. Here's my point. This you could not do, but these you can. Why? Because these are the right form, right? P is equal to blah, blah, blah. P is equal to blah, blah, blah. The derivative of P with respect to blah, blah, blah. You see? Friendly, not friendly. Doable, not doable, but they're the same. All right, now, let me actually just do this and end here. So here's our minus sign, and you can just practice on your own because, well, if dp dt is not hard. That's r over vm, and then I've got the next term, plus rb over vm squared. Okay, so I'm doing this. Here's the minus sign, and just put that out here. And the derivative of p with respect to t is very simple. Notice that the fact that vm is constant actually doesn't do anything. That's actually more often the case. Okay, now I've got on bottom dp dvm a little bit harder, a tiny bit harder. I know that the derivative of 1 over x is minus 1 over x squared. I just have to recognize that my x is now vm. Okay, and then I've got, unfortunately, the same thing over here, over vm. Okay, there you go. Did I get that? Yeah.